My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from Canada. So hope you are well and safe from corona pandemic. So we are trying to adjust with this new normal situation. So all we know that we cannot continue our normal academic program inside the campus. So we have to start our online program to continue our academic program. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology has already started its online program, including International Physics webinar. We have successfully completed our 123rd International Physics webinar, including 2 Nobel laureate physicists. And today it's our 124th International Physics webinar. So today is very important day for our department. Today I'd like to welcome you to a joint session between the Department of Physics, Pabna University of Science and Technology, and the University of York, Canada. And we have with us here today Dr. Isaac B. Smith, Assistant Professor, York University, Canada, and he has already connected with us. So I'd like to welcome our speaker. So, sir, good evening and good morning to your part. Thanks for accepting our invitation, sir. We'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation in this corona pandemic situation, sir. So the main aim of our program is to motivate and encourage our students in this corona pandemic situation. And thanks that you have accepted our invitation, sir. So, sir, you can start. It's your time. You can start your session, sir.
Okay, thank you very much for having me. I'm excited to speak to a group of people I've never spoken to before. And
yeah, it's my pleasure, sir, to host you.
Thanks very much. As you mentioned, my name is Isaac Smith. I'm a professor at York University in Toronto, Ontario, in Canada. And my research works mostly with ice on Mars. Are you able to see my slides, my screen? Just to verify.
Yeah, we can see.
Great, thanks. So my title is From Ice Crystals to Ice Caps, and we're going to discuss everything you see here, and then we're going to get down to very small scale to see ice crystals growing in my laboratory. I wanted to highlight this photograph. It's a beautiful photograph covering the North Pole of Mars. The North Pole is approximately where you see my pointer. There's a North Polar ice cap we call the North Polar layered deposits. It's mostly white, but it has these dark brown troughs. These are depressions that curve for hundreds of kilometers. And then there's a giant canyon there called Chasma Boreal. It's about the size of the Grand Canyon in the United States. And then around that, you see this very dark patch of sand. And this sand is moving every year, so it can move meters per year, similar to sand dunes on Earth. And that tells us there's a lot of wind. And so we can see even here clouds coming off of the ice cap that show the wind blowing the clouds out around. And then there's actually the start of a vortex here. Out past the clouds, you can see more ice, and you can see the limb of Mars. This is the edge of the planet, and there's a very thin atmosphere there. And so the atmosphere and the ice and clouds all interact together to create the climate system on Mars. And I'm going to talk to you about that. This was an image taken by the high-resolution stereo camera on the Mars Express mission. An important frame of reference is to look at the topography, because the topography drives so much of what happens on the planet. So it controls a lot of things, including, of course, some of the weather where the ice caps are. So here we have a global topography taken by the Mars Orbital Laser Altimeter, we commonly call MOLA. And in it, you can see very large volcanoes. You can see a giant canyon. You can see very large impact craters. And then in the north, you can see a basin. The north itself is a basin. And then in the south, you see these cratered terrains that are higher in elevation, where the dark colors are low elevation, so -8 is about there. And this cuts off at white, but these get to be 21 kilometers above average. Average is 0, that's about yellow. And so the average of the planet is somewhere kind of on the boundary of the two, the north and south. In the polar views, so this is North Pole, and this is South Pole. We notice the North Pole is in the dark color, so it's lower in elevation. On average, it's closer to -5,000 around the North Polar cap, But the North Polar Cap itself is about minus 2,000, and that's again below average. And then in the south, you see that we have much higher terrain, so between 1 and 4,000, so 1,000 being here and 4,000 above average for the center of the South Polar Cap. And of course, there's lots of craters, as I mentioned in the last slide. And here we see very few craters. And typically, planetary scientists think of cratering as a proxy for the age of time that it's been on the surface. So something like the moon has a lot of craters, and those craters are there because the moon has had the same surface for a long time. And that's a little bit like the south. Where in the north, we see very few craters, like on Earth, and this tells us that the surface has been changed recently, or at least recently compared to the south. So this is an old surface, but not nearly as old. So maybe a billion years instead of 3 billion years. And it's very difficult to see the outline of the South Polar Cap because of this high elevation. So I put this as a rough estimate for the outline. And we'll talk more about that in a second. The elevation change between high and from high here to low there gives us different climate perspectives. And so here we have higher elevation means lower pressure. And so the ices there should be less stable. It turns out they're not actually less stable in certain circumstances. There's another thing that happens. The North Polar Cap is almost entirely contained within the 80-degree latitude, but the South Polar Cap has an extension down to about 72 degrees latitude. And that means there's this entire section here that has climate and weather that happens earlier in the season. So early in spring, this will have a lot of activity, but there's no corresponding ice in the north to give you that. So the weather patterns are different, in part because of the elevation and then this latitude extent. So presently we're blessed with high resolution images of Mars. This is one taken from Hubble. And you can see great detail. You see lots of craters. You can see color differences with the reddish kind of orange hue versus the darker hue. And if you're unfamiliar, the red is primarily because of iron oxide or rust, just like we see rust on Earth. But the darker areas are places that have less rust, and it's more volcanic in terrain, usually. And so these are younger rocks that were formerly parts of volcanoes. There are also places on Mars where we see craters that are filled with dark material. That's that dark sand I mentioned in the north. We see lots of other striking features. For me, the limb is very important. This is a cloud that's on the nighttime side, just peeking through. We see also the South Polar Cap. This is the seasonal cap, a cap that only shows up in the spring, or I'm sorry, in the fall and winter, and then it goes away in spring. And in the north, we don't see that because this is the northern late summer. And so what we see is a cloud formation we call the polar hood that sets up in late summer. Previously, even going back to the 1880s, we have some images of Mars. These were taken with plates. They were not CCDs. They were not photographs. They were photographic plates. And astronomers were looking at the rotation of Mars to figure out the rotation. They were also looking at bright things that changed. So here we see the North Polar ice cap as it changed through time. And so this gave them the idea that Mars had seasons, even as far back as 1890. And so this is pretty interesting that they knew Mars had weather patterns and seasons like Earth does that far back. And so in 1907, we got better imagery with better telescopes. And you can see here the season changes a lot. And so this is the pole shrinking to almost nothing, and then it grows again. And so we can tell that Mars has lots of weather. And you can even see these really dark patches of that more recent volcanic terrain and the light patches that are the rusty iron oxides. They can get the rotation rate. They can get a lot of detail for this. And you can imagine that if you think Mars has weather and seasons, that it would lead people to believe that Mars also had people. And so for a long time in the early 20th century, there were lots of books and science fiction stories written about a Mars that had people and canals. And the canal happens to be a bad translation from canale, but this led humans, people on Earth, to believe that all these things were forming. And so they thought Mars was very Earth-like. And in some ways it is very Earth-like, but not in the way they were thinking. And so this was probably the most up-to-date map. Here we have south up because this is the way the map was drawn. And they have, the Hellas Basin. They named some of these features early on. Hellas is one of the biggest features on Mars. And then you have the Syrtis Major's there, the ice caps. And so this is a map from Antoniadis mapping, and this is the actual Mars. And you can tell now that none of these canals exist. Mars does not have water running around the surface. So that Hubble image is great, but we didn't have Hubble images. We had Mariner 7, one of the first spacecraft to go to visit Mars. And here we see the seasonal ice caps even better. You can tell that it's not a perfect circle. It has some rough detail. You can see some of the craters better that were impossible to see before. But still, we didn't have a great amount of detail. And so when we have Hubble, we have a ton of good stuff. And we can even see here 2 moons of Mars. So it's clear that there are 2 seasonal caps that come and go. And so, yeah, here's the north and here's the south. And it's kind of dusty. And the north and south cap grow and shrink depending on the season. So here's an image where we start with north, with mostly covered by ice. And it's going to go into spring and summer where this will retreat. And then this will grow. And so this is the polar stereographic view of the seasonal caps taken over a Mars year and then repeated and looped. So this is how the seasonal cap grows. Now the seasonal ice is carbon dioxide. It's not water ice. There's only a very small amount of water ice that moves to the ground like this. So the vast majority is carbon dioxide, and it's about 1 meter thick. So you have 1 meter of ice that covers the poles, and then it's thinner out towards the margins. All right, so that's the seasonal ice. That's really important for the climate of Mars because approximately 1/3 of the entire atmosphere collapses onto the winter pole. And so that drives a lot of wind, it drives a lot of thermal changes, and it's really critical for our understanding of Mars. So here's the south polar cap again. You notice there's no seasonal cap. Instead, here we have what we call the residual cap. This is the South Pole Residual Cap, SPRC. And it covers a small area. The other area would be much larger, way past here for the seasonal cap. So this is permanent ice. It's there every year, although it changes slightly. And I want to zoom in to show you some more detail. And here we have the South Pole Residual Cap in white, that's carbon dioxide. And then there's this red ice that's covered by dust. So the vast majority of what you see, included in this boxed area, is water ice, H2O, that's covered by dust. It's the same color as the dust in the surrounding terrain, and so it makes it hard to see. And I've put a star here to identify the South Pole. And you'll notice that the South Pole, even though it's the center of the planet, is not the center of the CO2 ice. And so this has actually been a mystery for a long time about how this, why this is offset from the pole. Here's some topography. It's not the best view, but it's enhanced quite a bit. But here we can see the South Pole is higher, not near the polar cap is higher, but not at the South Pole. The highest elevation is about approximately here. And then we see these steps down, and the steps correspond to these spirals that aren't as organized as the spirals in the north, but they are somewhat organized. And then if you go outward, you see the South Polar Cap sits kind of in a basin or partially in a basin. And then beyond that, there's mountains and craters and everything. So the CO2 ice seems to be just a surface layer. Here it is, the South Pole Residual Cap. It's that surface layer. And it has a lot of great detail. You can see a lot of these smaller spirals where we have exposures of the ice that's not covered with the fresh, bright white ice. The fresher ice is pretty young, where the darker stuff is older. And then in the big ones, we see water ice exposed. So water ice is the main constituent, more than 99% of the entire South Polar Cap. But the white part is also really important. We'll zoom in here, and And we can see some detail from the context imager, the CTX camera on Mars Reconnaissance Orbiter. And here we see where there's water ice. That's what this S shape is. And then to the left and then to the right, we see where we have the CO2 ice on top of that. And the CO2 ice sublimates and it creates these interesting shapes all over, and some more over here that are smaller. And we call this Swiss cheese terrain, named after the type of cheese that has lots of holes in it in American English. So here you see a great detail. Now, some of your eyes may have trouble seeing this. This is a plateau where my pointer is, and this is the low point where the pointer is. And this is a mesa or a plateau, and then here is low. And so it's important to know that the sun is coming from the bottom right. And so you can tell that here, and then you see these as pits versus raised sections. Another type of terrain, this is from the High Resolution Imaging Science Experiment, or HiRISE, also on Mars Reconnaissance Orbiter. Shows this thumbprint terrain, and you can tell it's named after thumbprints. And this stuff evolves, and so it has one side that is moving more than the other side, and so you can build up in height, and you can change the shape of these things. The sun is coming from the top right in this image, and so here you can see kind of a pit. So this is involved with the Swiss cheese. There's other types of pits too. This one's large, bigger than a kilometer. There's several of them. And these are sublimation pits that go into the carbon dioxide ice, and they make big bowl shapes, similar to craters, but they're not formed by impact processes. They're formed by sublimation. And here we see water ice with layering. Every time you see layering on the South Pole, you're going to know it's water ice, where the CO2 doesn't have layers. It's less distinct in that way. Here, if you zoom in, if we had zoomed in, we would see some of that type of Swiss cheese stuff. So here's the two types of sublimation pits together, where we have a big sublimation pit that's hundreds of meters deep, and we see these sublimation pits that are only about 10 meters deep. And you'll notice that the white ice, the fresher young ice, is on top of the this type of terrain, which is, we've learned, it's water ice on top of carbon dioxide. So there's thick carbon dioxide here, but it's covered by a thin unit of water ice, about 1 to 2 meters thick. And it creates these polygon shapes. You can see the shapes here underneath the white ice where it's exposed. So this is buried CO2, and this is carbon dioxide on top. How do we know this is buried CO2? When we go to Mars Reconnaissance Orbiter, this is what it looks like in an artistic rendition. And we use the shallow radar instrument, where Charade is the antenna you see here, plus some electronics inside. We're going to fly over Mars. In this image, you can see the radar shoots a signal down, and then it records the reflections as it crosses over the North Pole, in this case, for the video. And it gives us the opportunity to see a slice of the cap. And so here we can see the layers of the ice cap exposed. They're not exposed, but they're recorded with the radar. And so these layers tell us a great story. You'll notice also that we have these troughs here. These are the spiral troughs that I mentioned earlier. And they're not this deep. Actually, this is vertically enhanced by about 100 times. And so they're not quite as deep as they look. And if you look closely, you can see that the layers here that we see in the radar interact with the troughs. And this will tell us some of the trough story. We'll talk about that later. So using that same instrument, the shallow radar, we can cross over the South Pole. And when we do, we see below the surface, just like we did with the North, we see some layers, not very many, and this is unfortunate. The South Pole doesn't respond as well to radar as the North does, except at the very top. And at the very top, we see this thick unit of what we've determined is carbon dioxide. So we have water ice below and carbon dioxide above that residing in those troughs. Remember, we have those depressions. Well, the CO2 ice is sitting in the depressions. And it has a little bit of reflections in here. And we believe that to be water ice. So how do we know this is CO2? We can't actually see it and we can't touch it. We use geophysical techniques. So we take the wave propagation speed of the radar. And by the way, the radar has about a 20 megahertz center frequency and a 10 megahertz bandwidth. And so we can use that to determine the wave speed through here, that this is carbon, it's the same as carbon dioxide ice. If we correct for the wave speed, then the layers of water ice we see here will get flat. And so that we know that we're right. And this tells us here that we have the sublimation pit. It's sublimating, it's entering into this thick CO2 unit. So this is how I know that the sublimation pit is CO2. And the water ice on top, we can see with spectroscopy that we have more CO2. So that explains some of the CO2 stuff. Using that shallow radar, we can also map out the extent of this thick, the thick CO2 here. This is very important thing that we've done in the last few years. So the dashed line was a map created by the USGS, the US Geological Survey. And I'm trying to understand these surface features where you have sublimation pits, where you have these guys. These are also sublimation, but they're linked to be spirals. And they mapped it out like that. We can also use the radar to map out the thickness of that unit that I just showed. So this thickness and the extent, you notice that it's not everywhere, it's only in a few places. And so this is where the radar was able to map out the thickness of the carbon dioxide, and it gets up to over 1 kilometer thick, but on average it's only 400 meters or so thick. You'll notice the yellow dashed line, the circle, this is the limit of Mars Reconnaissance Orbiter. So outside this line we have great detail and data. Inside the line we have no data, and we can't use this. So this is an extrapolation, but it's not a very good one. So we're working to make a better extrapolation for that. To do this, we used the shallow radar, the Charade instrument, and we made a 3D volume. So this was done primarily by Than Putzig and Fritz Voss at the Planetary Science Institute. And we can see the bottom of the ice. This is with the 3D. So we made this map with the 3D. You see the bottom of the ice. You can see what we call bounding layers, BL2, BL1. And we can see this from A to A prime, that's this top one. And then B to B prime, this is bottom one. So what do we think happened? We think there was carbon dioxide that formed first, and then this bounding layer of water ice, more carbon dioxide, another bounding layer, more carbon dioxide, and finally that thin bounding layer that we saw on the surface. 1, 2, 3. These are 3 distinct periods of climate where we collapse the ice there. And so what we have is now, we think, a climate cycle. And so the next step was to identify that these carbon dioxide deposits that are up to 1 kilometer thick are flowing like glaciers. And so we have some high topography, we have ice, and it wants to flow downhill. And you can kind of tell in this image the ice wants to flow downhill. And so that's what I'm showing here. And we want to test the idea of if this carbon dioxide can flow. There's been some experiments done by Bill Durham and more recently by colleagues of mine, Cross et al., to show that the carbon dioxide, which is in the cylinder in this case, flows more readily. So it's more viscous, less viscous than water ice. And so it can flow like a glacier. Nye et al., this is John Nye, suggested that the CO2 would flow too fast. If it flowed too fast, then it wouldn't be able to hold its shape over long periods. And so it's 100 times less viscous than water ice and flows too fast, actually. So we wanted to redo the experiments. And this is in a lab, this is Cross et al. At the University of Pennsylvania. It's a project that I helped fund, where we made carbon dioxide ice inside of a liquid nitrogen chamber. We pack that into a cylinder like this, and we make these cylinders of CO2 ice, and then we push it, we squeeze it, and we see how it responds. And so using that at different temperatures, we can get the exponent. So this is the strain rate over the stress, and this is the equation for flowing materials. And so if we know the stress and the strain rate, we can get this N. That's the N that goes right there for the stress exponent to give us the strain rate. And we've confirmed that carbon dioxide does flow more quickly than water ice at certain temperatures. And with this high exponent, it flows very strongly on steep slopes. All right, so this is the most recent one that was published actually in 2020, so this needs to be updated slightly. Okay, so I want to point out that there's some morphologies here consistent with glaciers also. So this is, again, the outer boundary. You can see the dashed blue line in this case, the no data zone. And then if we cross here with topography, that's the MOLA instrument again, we can see there's a dome shape at the highest point. And I hope you can see this. You can think of CO2 on a flat surface like a cookie that wants to flow down and melt and give you this dome shape. So this is a very common shape when you have fluids that flow on a flat base. Another type of morphology we see, starting from here and going down, is what I might call an alpine glacier. So this is Saskatchewan Glacier. There's an ice sheet here, and there's an outlet glacier there. And you can tell that it has some of these parabolic lines. These are topographic profiles. And here we see a very similar topographic profile in these parallel, and they're curved like this, like a parabola. Also, the topography of this one shows that we go from high to low. We also have this convex up profile, which is similar to other glaciers on Earth. There's some secondary evidence. So in this one, we see the layers. That tells us there's water ice. And here we have CO2 again. And we see these things that I'm calling compression ridges near the edge. Here's some more compression ridges. And this is a photo I took in Antarctica. And you can see here these compression ridges on the same scale. So they're a few meters tall, and they're spaced by tens of meters. And what happens is when you have fast-moving ice next to slow-moving ice, you can build up these compression ridges. And so that's what we see, where we have fast-moving ice coming towards the slow-moving ice in Antarctica at McMurdo Station. And we see that here with the CO2 glaciers. To measure this, I'm working with a student, Ignacio Isola, and then the creators of the ice sheet system model from JPL. And we have, these are our topographic data input. And you'll notice that we don't have very many points here. This is because we don't have much data, so it's not that valuable in simulating. But we do have topographic data. We have lots of cells. And we calculate the stress between every cell, vertically and horizontally. This is, like I said, the topographic, so the surface profile, and here's the thickness profile from that mapping that we did earlier. And so we have the thickness and surface. We can calculate all of the stresses on this ice. And we can input the values from our flow laws that we derived in the laboratory. And so we've been able to show that this outlet glacier, like I was talking about before, flows at a rate that gives us this topographic profile. Now this is actually the velocity profile, but velocity will give you the topographic profile. And so this matches what we expect to see. But we can see kind of here the ice is flowing down like a glacier, like I showed in an earlier image. And here's a snapshot, so a smaller view of our input topography where we zoomed in on this section. And this is the input topography. And then over time, we can watch it change. So we're adding ice here, and it's going to flow into that. Here you can see it flowing into the valley. As enough ice forms, it's going to go over the edge into another valley, and so then you pick up a lot of speed here. And eventually, you end up with, if you keep growing this ice, something that looks like the current deposit. So I wanted to show that. Okay, so this is a view of that same input topography, but looking down the glacier. And so this is the input topography, and then the simulated Mars, and here's the actual Mars. And so the glacier here is flowing in, and if we put our inputs right, we're going to get something that looks very similar to this. And so the surface contours, as I mentioned, here we have the parabolas, here we have parabolas. That's very similar. Okay, so that is the CO2 glacier story, and that one is in review right now. And so I hope to have that published in 2021. Back to this image, we have we're back to the South Pole residual cap. Here's the South Pole again. And we're going to motivate some experiments that we're doing in my lab right now. So the South Pole residual cap doesn't sublime in summer because of a changing albedo. What do I mean by that? So here we have some images of the South Polar cap, residual cap, taken at different times a year. And you'll see that sometimes it's brighter than others. So Lambert albedo is the reflectivity. So sometimes it's close to 0.8 and sometimes it's only 0.6. And this is depending on time of year. So as we go through a full season, we go low reflectivity to high reflectivity and back down to low reflectivity, and so on from one year to another. And this strange behavior makes it so that the CO2 ice can persist even when the summer gets very hot. So southern summer is hotter than northern summer, so you'd expect the CO2 to be gone because in the north the CO2 goes away. But this changing albedo that's related to the intensity of the sun actually protects the CO2. So that's one motivation. Another motivation is that we can form CO2 ice on soil. So this is from the Viking 2 lander. You know, this is very rocky, but there's also the CO2 ice that formed in the late summer and early fall. And so this tells us that we have CO2 interactions with rocks. And then here's another image that is motivating some experiments. Here we have the typical kind of red Mars and then the black sand dunes on top. And the sand dunes have this kind of a beautiful shape. And here the sun is from the right, upper right, and the sand dunes are moving mostly to the right. So they give us these slip faces. If you're a geomorphologist, you'd recognize this as a slip face. This is the back of the dune. The dune is marching to the right. But this is taken in the summer. If you come back in the wintertime or in the springtime, you get a very different view. So again, these are dunes, just like this. And you can see the slip face here. So they're moving to the right, just like in the previous image. Here's another slip face. But now they're covered with carbon dioxide frost. And you can tell, so it's kind of pinkish, white. If we go back to the Viking, you can see now why it would be pink and white. It's because we're mixing the red color with the white color. And so these dunes are moving like this. And that's, they're frozen in place now with CO2, but it's really cool to see how it looks differently. So here we have the crest of the dune, and you'll notice that there's these dark streaks coming off of it. These are just streaks. They may look like a tree, but they're not a tree. It's on the surface. I'm going to zoom in on this one, and you can actually see one of these in action. There's a dust plume, so this is in the atmosphere, above some of these streaks. So these streaks are caused when the CO2 ice cracks, it breaks, and then you have gas expelling material out. That's where some of this dust comes from. I'll explain more in a second. Here's an image, and this is one that takes through time, so we can watch it go through different time steps. And so these streaks are growing on the back of a dune. And here's a panel of 5 images. This is in the south, but it's very similar, where you have the same location, and you can see that there's almost no dark spots on the dunes, and then they grow and grow and grow, and eventually the whole dune is covered with these dark spots. So that's a motivation. And then the seasonal CO2 frost gives us its own motivation, where we have some places that are bright white and some places that are dark. And I'll explain why that is. So we're going to zoom in on this spot. This is, by the way, from the Marcy camera, Mars Color Imager. And then we're going to go into a high-resolution stereo camera image, HRSC again. Remember, the high point of the South Pole is here. The South Pole itself is about there. And we can see some bright white ice that's associated with the residual cap, but it's actually covered with the seasonal cap. There's lots of beautiful detail here. We don't have time to go into all of it, but you can notice that there's the red and white interacting, making a pink color. There's also these darker colors. So this is a zoom in again, and you can see even more detail. Some of these streaks are happening in the troughs. We're going to zoom into this spot with the green star. And now we're looking at an image from the thermal emission imaging system we call THEMIS. And you can see a trough here and a trough here. And you can tell that there's a lot of activity. And this activity is caused in part by wind and in part by these eruptions that I was talking about a second ago. So you have an eruption and the wind carries it downstream and creates these streaks. And the streaks follow the topography because the wind follows the topography. So these are really beautiful images showing how active Mars can be at the South Pole in the springtime. Now, how do these form? The mechanism, we call it the Kiefer model. Is Hugh Kiefer came up with it about 20-something years ago now. And that is, you start with a dusty CO2 frost. So this is the seasonal frost. In the summer or in the springtime, it gets sun on it and it changes to a translucent slab. And I'll show you some of that in my lab. You build up enough pressure underneath because the sun can come through the translucent slab. So here it is again. Sun goes through and it warms up the bottom. When it does, it creates pressure. That pressure pushes through the ice. It breaks the ice in a fracture. And it brings the dust that's down here on top of the surface. And so you get this deposit of dust. So that's what you're seeing here, where you have this eruption and bringing the dust in. And it creates what we see there. And so here's another example where we have the dark streaks and some CO2 ice that's recondensing on the surface. We actually see that in this image where you have the bright stuff and the dark stuff together. And this is an artistic rendition of what we think it looks like, where you have CO2 ice and you have these eruptions, and sometimes the wind will blow it downstream. And so here we have these right there. Here's some more examples. And you'll notice in these examples, I've chosen these because they highlight fractures. So the CO2 ice fractures, and it gives you the fractures or the source location for this dust. This is a paper from Anya Portoikina in 2012, and she highlighted the fractures. And here's an example where you see the 50-meter scale bar, and you have tons of fractures inside the CO2 ice. And of course, some of these streaks, and she's mapped them there. And yeah, and here's some more of these fractures. Another cool feature is what we call spider. Spider is similar to what we saw before, but it has a connected network underground. And so these are individual splotches or fans, but they form in this network, and you can kind of see the network. And that's because the gases travel through a network underground when they're buried by CO2 ice. Here's another example of that. So this is the huge example. These are smaller examples. And you can see why we call them spiders. And some more. If you come back in the summertime, these are actually topographic depressions. And so the ice and the gas and dust flow through the tendrils here to the middle, then they erupt. And then you can check out the order of these and kind of get an idea how old they are based on the order of the network there. Okay, so this has been shown in a laboratory experiment. Laura McCohen did some experiments where she put CO2 ice on top of sand inside a chamber, and she was able to form these spider-like features. And it's this gas escaping through the CO2 ice. I don't have videos of that. And then here's a chamber that my lab is using. So this is in my lab at York University, where we have liquid nitrogen pumped into the chamber to grow ice crystals. And so this is my previous chamber, and we have a new chamber that we're building right now to do more of these experiments. So we can control temperature and pressure some, and we can input CO2 gas. So we form CO2 ice inside and input CO2 gas. And this is a diagram of what we're looking at. It's not important, but we have all the detail, but we have the vacuum chamber. We run things with a computer, our CO2 cylinder that you see there, goes through a pressure regulator and puts gas in. We have a vacuum pump and a pressure gauge to control, help control the pressure inside. And we want to maintain a pressure It's equivalent to Mars, so approximately 7 millibar. And then our nitrogen provides the cold for the cold plate where the CO2 is going to freeze. And this is the cold plate. And already you can see some of the ice crystals we're going to grow. Anja Porchankina had done some experiments. This is at a lab in Denmark. And so this inspired me to build a chamber and do some of the similar experiments. She had results that looked like this. In trying to understand the way crystals behave, she did experiments at different pressures. So here's 1 millibar, 7 millibars, 55 millibar, and for different durations and different temperatures. And she found a wide variety of types of crystal structure. And my lab is busy trying to reproduce this. She also found transparent ice that fractures. Just like we see on Mars, we see these big fractures. These are much smaller, so we're talking order of millimeters and centimeters instead of meters, but we can still see that the ice fractures. And so this is transparent ice. It looks like there's nothing there, but it is there. And here's a zoom in on the fracture. And if you put light from one side, you can see why you get this really reflective property, this maybe high albedo caused by the light. Here's one of our experiments where we create fractures in my lab. And you can see they form very quickly and then they heal very quickly. This is during deposition. And here's another view of it from above. And so you see these fractures forming and happening. Now this is only 3 times sped up. So this is every second these things form and then they go away. So this is at t equals 0 seconds. This is t equals 1 second. You can see that all the fractures here start to heal. And there are no fractures here, but then they are. 1 second later, these have healed and these form again. So this is actually at higher pressure. And 2 students, Roshana Karimova and Adriana Van Brennan, have been helping me with this. So slightly higher pressure, we're now going to really controlled low pressure. And we see fractures, but not quite as rapidly. So that has to do with the thermal gradient. As you deposit very quickly, you create this steep thermal gradient. And then if you do, the CO2 ice doesn't like it and it will fracture. Okay, this is a very recent experiment taken in December. And we're growing small crystals like this. The crystals grow to pretty big. They can be like 5 millimeters or so, or even bigger. We use this, this is a tetrahedron for scale. And it's sped up and then slows down a little bit. So I'm gonna accelerate, but you'll notice the time here. So we're only moving in seconds. Okay, here we grow. We get these very large crystals. Eventually they're gonna join. And when they do, they can center and they can form a larger crystal. They may or may not have boundaries. And so one of the things we want to test is how these things form boundaries. And then can we get rid of the boundary? Now the ice here is only a millimeter or so thick because we're growing very slowly. We'll speed it up a little bit. And here, so now we form solid ice. There's no gaps anymore. And then we're going to turn the heat on and see what happens. And you'll notice that the surface gets kind of fractured, but it's also quite transparent. The brightness we see is from our camera, or from our light source. But the ice we can still see all the way through the bottom. So it's a very transparent ice, just like we've noticed on Mars. And so these are pretty cool crystals. The thing we're doing now, we're doing 2 things. We're going to start doing long duration experiments to where we can grow the ice very thick. And also we want to measure the reflectance spectroscopy at different angles. Because we've never done that before in a lab. We only have measurements on Mars and we want to compare to that. Here's just another view from slightly zoomed out of these crystals forming. And eventually they'll grow together or frost over. So in this case, we frosted them over. And it really depends on the pressure and the temperature. Here's kind of a final state. This is the same cold plate, but in our first chamber. Okay, and we also, like I said, we want to measure the spectroscopy at different angles. There's not been a lot of work, so this is old. There's a 1969 paper, there's a 2005 paper, but there's not a lot of work being done on the spectroscopy of CO2 ice. And so we want to measure the reflected spectroscopy. You'll notice that CO2 has certain absorption coefficients, certain parts where they absorb a lot more, and these are unique identifiers to CO2 ice. And so we're going to look at those. And we really want to understand why the albedo changes. It might be due to fractures, but it might be due to something else. And so we want to understand this in our lab. So we're going to add light sources to hopefully be able to change the albedo. This is coming in the next years. Okay, so I've used a lot of time. I'm going to go back to the North Pole and talk about some other work we're doing. If you remember, this was the first slide I used, and we're going to go and talk more about the spirals. So here we have the giant spirals and this Chasma Boreal, the giant canyon. The spirals themselves have a wavelength of about 50 kilometers, although that varies depending on location. And the depth is 400 meters in some places, and even 1,000 meters in others as you get closer to the outside of the polar cap. And then there's wind streaks you can see right here. Here's some wind streaks. There's another wind streak. There's some here that are more faint. The wind is actually the driver of everything that we see happening. Here's more wind streaks. The winds create this shape. Let's zoom in on this spot. So here we have a CTX image of, we got the white plateau. So this is the white plateau, dark, and then there's an intermediate color, and then another plateau. So here's the two plateaus. Here we have the dark layered terrain, that's water ice again. And then we have what we call banded terrain. So layered terrain and banded terrain, where the layers experience erosion and the banded places experience deposition. And so here's kind of a view, not of the spiral, but of the canyon. And you can see there's lots of layers here. And there's even detail that would tell us about a climate record of erosion and new deposition. And so part of my group is working on understanding the accumulation of the North Pole, because that's probably the best climate record on Mars, the North Pole. And so here's a plateau. The shading is kind of interesting because of the light, but I'm going to zoom in on these layers. So you can see layers. I'm going to zoom in again. So you see a lot of detail, and I'm going to zoom in one more time and get even more detail. The finest layers we see are about 1 meter, but that's from orbit. That's a camera that's 300 kilometers above the surface. We believe that there's finer layers that are beyond our resolution right now. And so we're going to look for that on the surface. One day in the future, we're going to send robots to the surface. Thinking about the spirals just a little bit, I mentioned earlier, and I showed you the video from Mars Reconnaissance Orbiter and how it can go across the cap and create these profiles. Well, there's a lot of detail in here. In the bottom, we see that the bottom of the cap is mostly uniform and flat. Now remember, this is 100 times vertically exaggerated. So the horizontal axis is 1,000 kilometers, and the vertical axis is 2 kilometers. So we're very much exaggerated this way. At the bottom, the layers are almost flat and parallel, but at the top, the layers get very deformed, and they're deformed in a way that matches the surface of the spirals. And so here you can see the spirals in detail, and here you can see the profile. So the red here is the crosscut of this profile. And the layers deform quite a bit, and this told us a story of the spirals, that the spirals have moved through time. We say migrated. So this is the bottom of a spiral now, but that bottom used to be over here. And the same thing is true. This one is the bottom of the spiral now, but it used to be over here. So these spirals have migrated through time. And we've been able to detect a climate change in the rate of change of the spiral. So the spiral is here, it used to be down here, and it changed. There's an inflection point at this kind of blue line. And so we're able to look at that and determine that there's been a climate change. We mapped it all over the cap, and we found this is the same everywhere. There's this unit, I'm calling unit D, ABCD, or the widespread recent accumulation package. published this in Science in 2016. And based on climate models that we didn't run, these are not our climate models, but a group said that there should be a climate change at 370,000 years. And so we think that for the first time, we've put a layer and an age together. So 370,000 years we think is the age of this unit, or of that transition. Oh, yeah, and we were able to map the volume of this and determine how much ice has moved between the poles and the equator. Part of the story with the troughs is to look at the wind. I mentioned wind streaks earlier. Here you can see the layers, so it's water ice. And you can see that there's wind coming from the high plateau and moving into the bottom. And at the bottom we see these clouds, this cloud. And so this tells us about the method where you can remove material from one spot and transport it to another. This sets up the migration process. Here's some more examples of that. So these were taken a couple hours apart. And I've stretched them so that you can see them. So you're kind of missing the layers here, but there are lots of layers. And here you can see that cloud forms. Like I said, they're only a couple hours apart. And this is the type of cloud we see on Earth. So this is from Antarctica, taken off. This is a photo taken off the Australian Antarctic Division website. And this is the same kind of cloud we would see in this image. So it's caused by what we call a katabatic jump from a fast-moving flow to a slow-moving flow with a high Froude number and a low Froude number. And then we form these clouds right above that. So this is a transition from erosion to deposition, and where it does, you create the snow wall. So we're eroding up here and depositing there, and that gives rise to the migration. Here's another image, kind of before and after. And here's another one in the same spot, kind of before and after. So I'm working with student Prithvi Acharya to identify these. And Prithvi's found that there's thousands of trough cloud detections. So the total number of images is in the thousands. The total number of cloud images is several hundred per season. And then we see some on the north and on the south. So they peak in late summer, where 90 is the the summer solstice. So this happens mostly right before the summer solstice. Prithvi's also mapping out the edge of the seasonal cap. He's doing a good job with that. We can track this. So I've shown the seasonal cap multiple times. So this is the north now, it's retreating. And he's looking at some of the details with these Marcy videos. Marcy is the camera that made this video. And you can see some great stuff happening where you have winds coming off, dragging dust with it. And then the change in brightness through time he's been looking at. And we've noticed that the clouds pick up due to the retreat of this ice. And so the clouds are really busy in this late season. And that's the katabatic winds. And then also we have the sea breeze effect, where we have bright ice that's cold, and then this warmer section out here. And so this accelerates the winds. So you get a really windy period. Something that Prithvi's noticed is a rapid change in the color of the surface. So here we have the North Poles with spirals. Here we have a dust cloud. And I'm going to go back and forth between two images that are taken about 20 days apart. And you can see there's this rapid change from light to dark. This has to do with all the dust being removed, dust and ice, through some very strong wind event. Here's another one. These are smaller events. But when we see these events, we also see dust coming off the cap. So it's very windy. Instead of being in spring and early summer, these are in late summer now. And here's another image where we see this change from bright to dark associated with the very windy period. Here's another one with the CTX camera. You can see the layers. And so the surface changes, and this happens over a matter of hours. In just a couple hours, we remove all that ice. And here's one with a very high resolution, and it changes very rapidly. Okay, so I've gone through a lot of many topics here, and I've used up all my time. So I want to invite anyone who would like to ask a question, and I'm happy to talk about any one of these topics.
Thank you, sir, for your nice presentation. So we have got a few questions in the inbox. So first was what is the seasonal cap?
The seasonal cap is carbon dioxide material that deposits in the springtime. Deposits in the late summer, fall, and winter. And then, so we can see the seasonal cap here, it's carbon dioxide. And then as the sun comes up in the spring is when it retreats. So we usually study it in the spring because the sun is up and we can see it then. So the seasonal cap is there. And then that's for the north. And I showed a video of the south and north together. So this is the north shrinking and growing, opposite the south shrinking and growing. So this is carbon dioxide, and it's about 1 meter thick, and it covers a large section of the planet.
Thank you, sir. There is another question. So what is the shallow radar?
Yeah, so shallow radar is an instrument on Mars Reconnaissance Orbiter. So this is Mars Reconnaissance Orbiter. Like I said, it's an artistic rendition. It's a video made at JPL. And here we can see it has the solar panels, it has the main communication antenna. There's a camera down below that's high-rise. There's actually multiple cameras. And then the shallow radar uses this antenna, it's a dipole antenna, to send a signal down to the surface and then reflect that signal back up to the spacecraft where it records the reflections. So it records voltage and time. That's all it can record. When it does, it'll record things that are in the subsurface because the radar wave can propagate below the surface to give us all the detail down here that we see.
Thank you, sir. So this may be the last question. So is it possible to grow plant in Mars in future?
That's a good question. I like that question. I think the answer is yes, for sure, but not with current Mars. If we took seeds to Mars and planted them, first, there's no water. Second, there's no organic material. And so the organic material you need in order to create the plant isn't there. And lastly, there's a lot of salt. It's very, very salty. And so what, as humans, we would need to do is take water with us or find water. Of course, we know there's water on Mars. Take that water, melt it. We have to bring some organic material with us, and we have to get some of the salt out because it's too salty for the types of plants that we like to eat. But eventually, we'll be able to grow food.
Thank you, sir. So there is another question. So this is maybe the common question from all of our students. So if any of our students want to study or to do research in this field, what she or he need to do for that? Yeah. Is there any remote program? So can he or she work from here to your group, or
that's a good
is
question.
There any?
Professors, I don't know about at your university, but professors at my university will mentor students and teach the students about how to look at the data, how to process it or analyze it in a way that helps them determine things, so make discoveries. And so the first thing is to get access to the data. And the good news is that all the data that you're looking at is publicly available. You can go to NASA's website or the Planetary data system and download the data. And so this is an image that you can download. This is an image you can download. Same thing here. And all of the radar I showed, you can go download that data too. That doesn't mean that you know exactly what to do with it. So you need to work with someone who has some experience. And typically, you could contact the professor and ask to work in that lab. So that's a possibility. Normally, that would involve moving to Canada or to the United States or to Europe where this is being done. But I know there are places in Southeast Asia. And so ISRO is the Indian Space Agency. You can work there. I work with a colleague there on actually radar data of Mars. And so there are places in Southeast Asia where it's possible to work on this too. But typically you would apply to join the lab and to move to North America or Europe to do this.
So thank you, sir, for your nice presentation and discussion session. It was a really great webinar for our students. So they have learned a lot of things about the the Mars pole and the ice crystal to the ice caps. So thanks again for accepting our invitation. So hopefully in near future we'll arrange another webinar with you, sir. So bye for today.
Yeah. Okay. Thank you very much for hosting me. I really appreciate this opportunity.
Yes, sir. So the main aim of our program is to actually motivate and encourage our students in this corona pandemic situation. You know that we cannot continue our normal education system inside the campus. So this is the only way we can motivate them. So we have successfully completed today 124th. So hopefully this program will continue. And so thanks for supporting us.
Great. Good luck in the future. And if you have more questions, you can email me, okay?
Okay. Thank you. Bye for today.